Okay, let's get started. Good afternoon, everyone, and welcome to the Generative AI Roundtable. I am Daniela Rus. I'm professor and director of the Computer Science and Artificial Intelligence Laboratory at MIT for CSAIL. And I am very honored to be your moderator today for today's discussion on generative AI from MIT CSAIL's perspective. Now, from the beginning of the AI field, MIT CSAIL has played a pivotal leadership role. Over the next few years, advances in artificial intelligence and robotics have the potential to transform not only academic disciplines, but entire economies. And as humanity works to solve problems ranging from climate change, curing disease, removing inequality, ensuring sustainability, eliminating poverty, AI opens the door to powerful new solutions. Many of the most powerful forces in our lives, electricity, running water, even government, operate in the background. We don't think about them most of the time. They are just there making our lives easier and usually better. But that wasn't always true. Once upon a time, these were remarkable innovations that were only available to the very lucky few. Well, today, AI has joined that list with the advent of extraordinary tools like ChatGPT, Bing Chat, DALL-E, Stable Diffusion, tools that are now in everyone's hands. The power of AI is growing significantly due to the sheer scale of data and computing, and also the ease of use. Now, within the broad field of AI, generative AI is a recent approach that refers to the ability of a generative AI system to create new data, similar to but different from the training data, without any human intervention. The data may be text, images, code, speech, or any other data type. And this is revolutionizing how we interact with technology. Generative AI is already in use in many industry sectors as diverse as retail, finance, healthcare, manufacturing, education, and so much more. And for example, it is used to design products that meet particular specifications. And this leads to more efficient and more customized designs that are better suited for customer needs. Generative AI is also used to create new content in the form of images or text and impacts how businesses communicate to their customers. Now, because we do not fully understand how it works, there is a tendency to anthropomorphize or even feel scared by generative AI. As famously said by Arthur C. Clarke, any sufficiently advanced technology is indistinguishable from magic, and generative AI can often feel like magic. Now, part of the reason is that it is hard to visualize and understand the scale of generative AI's power because it is so different from human scales. We are used to thinking in feet, meters, miles, hours, seconds, minutes. Well, with generative AI, the size and time metrics are beyond human scale. For example, the training of generative AI models take billions of data points, and my colleagues estimated that training Minerva on a supercomputer would take an astounding 130 years. The amount of data used to train the generative models is usually massive. And I want to give you an example of how this works. I recently received a wonderful present from my students Alexander Amini and Ava Soleimani, my AI-generated portrait in the style of classical painting. Okay, now, to get to this portrait, Alexander and Ava trained a model on 5.8 billion images, and these images were accompanied by their textual descriptions. So on these 5.8 billion images, the model took about 2 to 3 months to train. After the training on this data set, the model was able to generate new human portraits, but the model would generate a portrait of a random person. So realistic but random portraits. Now, in order to personalize this to me, Alexander and Ava employed a secondary training regime, which they fine-tuned on 10 of my photos. And these photos were also conditioned on the text description of Daniela Rus. This training took about an hour. And as a result, this is what they can generate. So here is my portrait, generated in the classic painting style. And here are a lot of other portraits generated alongside with that. Also, new images that never existed. Some resemble me more than others. But it's really extraordinary to think about how you start from 5.8 images, 2 to 3 months of training on your machine, 10 additional pictures, and that's what you get. So I hope this example gives you some insights into the extraordinary power of generative AI. However, as with any new technology, there are also concerns surrounding its use. One of the biggest concerns is the potential for these models to be used for malicious purposes, such as generating fake news or deep fakes that can be used to manipulate the public opinion. Another concern is the potential for these models to perpetuate bias and discrimination, as they are only as unbiased as the data used to train them. So in today's roundtable, we will demystify generative AI by discussing how generative AI works, what it can and cannot do, how the research community is addressing what it cannot do, the potential for generative AI to be used positively in a range of applications, and the concerns surrounding generative AI. Joining me today are a distinguished panel of experts in generative AI from MIT CSAIL, Professors Phillip Isola, Jacob Andreas, and Armando Solar-Lezama. We will start with brief presentations about generative AI and its use in generating images, text, and code. And next, we will discuss the questions you submitted with your registration, organized as technical questions and societal questions. I'm looking forward to a lively and insightful discussion and hope our conversation will shed light on the important issues surrounding generative AI. So, Phillip, I would love to have you start us off. Can you explain to us how is it that Ava and Alexander were able to generate my portrait in classical painting style? Over to you.
Hey, thank you, Daniela. OK, so I'm going to start the presentation on generative models of images. I'll talk a little bit about the model that was used to make Daniela's portraits. And let me just hook up my computer. Make it full screen. There we go. OK, so I'm going to talk about generative models of images. I'll try to tell you the basics of what they are, the basic input-output usage, and then I'll mention one way that you can train them. OK, and that's an image made by a generative model, which, of course, will have a lot of illustrations like this. OK, so I'm going to start with something that you might be more familiar with, which is classifiers. So this is something that is all over the place in data science. If you've ever taken a machine learning course, you've seen a classifier. A classifier is a function that will try to assign labels to data. So in computer vision, we use classifiers all the time. We want to recognize that cartoon of a bird, so the classifier should classify it, should label it as a bird. OK, I want to start there because you might be familiar with this, and if you are, then generative models are not so hard to understand because they're just the inverse of a classifier. OK, so in a generative model, what you do is you start with some description of the content you want to generate, like in this case, the label bird. And the generator has to make up some data, an image, that matches that description. OK, so this is like the inverse of a classifier, but things in this direction are a little bit different, a little bit harder. And the main reason is because there are a lot of different photos you could have generated that all would be considered bird. Why did I pick that robin? That's arbitrary. It would have been fine to put a parrot instead. So generators need to not only take in some label, they also need to take in something that will disambiguate this mapping. And the usual way they do that is they take in some noise. Think of this noise as being like rolling the dice, and how the dice come out determines which photo I'll generate. OK, so if I do one roll of the dice, I will get the robin. And if I do another roll of the dice, I might get this blue bird. Another roll will be another bird. So you can think of these dice rolls that are input into the generative model as noise. It's often called noise. We'll see that it's also often called a latent variable. But it's like specifying all of the things that are not specified by the label bird or whatever other instructions I put into the model. Okay, so let's look at those dice in a little bit more detail. In typical generative models, I won't just have 3, I might have 100 of these dice. This is a vector of random variables. So a vector of dice rolls or other random variables. And each element of that vector, every single die, will control a different property of the generated imagery. So if I roll the first dimension, if I just randomize the first dimension, that might correspond to the color of the bird. If I change it, if I roll again, I'll get a red bird. If I roll the second dimension, that will control a different attribute of my generated imagery. That might control the angle. If I roll the third dimension, maybe that controls the size. And then remember, there's 100 of these dimensions. So they all specify different attributes of the generated imagery. And there might be a dimension that controls the shape of the bird's beak and so on. And this is how, when you roll those dice, you get a different but realistic looking bird. Okay, so you can just roll the dice and get a random bird, and that's one thing that we use generative models to do, make up random photos, make up random stories. But I think that's actually not the most exciting thing. I think the much more exciting thing is that you can control the imagery that you're generating or the content you're creating by manipulating those dice, by manipulating these noise inputs to your model. So rather than thinking of them as dice, I like to think of them as knobs, okay? So there's a knob, which is one dimension of my input vector to my model, and that knob might control the color, and I can randomly spin that knob and get a random bird with a random color, or I can set the knob continuously to change the color, and as the user, you could intervene and do this and make images that you like for your application. And a lot of the current generative AI applications correspond to different ways of controlling the outputs via these knobs. Okay, so that's the basic input-output relationship in these models. I want to not just show you cartoons, but here's an example of an actual real model. So these ideas are relatively new, but not that new. This is 2018, and you already had models back then. This one's called Big GAN that could do this. Okay, so in this model, we have on the left, we have the set of knobs, and they define this set of controls to the generator. And in that setting where you are manipulating these controls, we often think of them as the latent variables that explain the data. Okay, and then on the right, we have our synthesized image. And if I take one of the dimensions and I tune it, I'll be walking in one direction in the latent variable space, and that will correspond to making a set of images that manipulate the presented image in one particular way. In this case, it's changing the bird's orientation. And if I tune another knob, that means I'm moving in an orthogonal direction in that latent space. And in this particular model, that corresponds to changing the background color. Okay, so these generative models, they're not just making like one isolated image. They're actually making this little snippet of the natural image manifold, this structured object that can be manipulated in interesting ways. It's this continuum of data rather than just randomly sampled data. Okay, so that's how generative models work. That's what they do for making imagery. Now I want to very quickly describe one way that you can train a neural network generator pictured here to achieve that kind of mapping. Okay, so the thing to keep in mind is this is just one way you can do it that's popular this year. I'm going to talk about diffusion models. They made Daniela's portrait, but there's a lot of other ways you can do it. They all share more things, and they're all more similar than they are different, really. And the big thing that they share is that they all learn to make imagery by downloading a lot of photos, usually from the internet, and trying to make, when you roll the dice, the output image look like the example training data, okay? So the common thing behind all of these models is they're trained on a lot of examples of what real images look like, so then I can tune the parameters of my model to make things that look like real images. That's the main concept. Okay, but let's go into a little bit more detail on diffusion models. So the way diffusion models work is they map from random noise to imagery. And they notice that it's actually very hard to create structure, but it's much easier to remove structure. So they actually invert this process. You start with images, and then you turn the images into random noise. And that turns out to be a much simpler process than starting with a random vector of Gaussian noise or dice rolls and turning that into images. To turn a structured object like an image into random noise, you just have to apply a process called a diffusion process. Okay, so diffusion processes are common in nature. They get their name from diffusion in physics. So imagine that these birds are actually ice sculptures, and I drop that ice sculpture into hot water, and it melts. So that structured object melts, and it becomes entropic, and the particles spread out all over into this entropic mass. And that entropic mass, that water that's diffused outward, is mathematically the same as random noise. So that's what diffusion is, but if I apply that on pixels, you start with an image, and you just add a little bit of noise step by step to corrupt that image. You add what's called Gaussian noise to corrupt that image until eventually, if you do this enough times, you get to a completely entropic random noise image. And mathematically, that has the same structure as a random sample from a simple process like dice rolls. In this case, it might be from a Gaussian distribution, just a slightly different process. OK, so diffusion models take all of your training data, and they add noise to map that training data into perfectly random noise. And then they simply train a model to invert that process. They try to turn times arrow backwards. It's like the hot water that's all mixed up recongealing back into structured ice sculpture of the birds. So they're trying to invert that noising process via a denoising process. And the way that works is you train a neural net F to simply remove a little bit of noise step by step until you get to a noiseless image after starting with pure noise. And that sequence can be trained via supervised learning because you have all of these examples of different images turning into noise. And now those are all supervised data for training the inverse mapping. So it's just supervised learning, which is something you might have encountered in a machine learning class. OK. So if I sample different random noise, that corresponds to a different random configuration of pixels that then congeal into one particular bird. If I sample other random noise, it will congeal into a different bird. And the last one will make my parrot in this example. OK, so really cute, simple idea inspired by physics or has an analogy to physics. And this is really how a lot of these models you've seen recently work. This is how DALL-E 2 works. So you input a sentence, a photo of a group of robots building this data center, and you also sample this random noise, and the noise congeals into these photos. And everything not specified by the text gets randomly learned and sampled via that diffusion process. So the lighting and the angle and where the robots are, that's all learned by this generative model. So that's one of the ways these models work for making images really popular right now. And I think Jacob will take over next to talk about a way you can do similar things, but with text.
Thank you very much, Phillip. Now, while Jacob sets up, can you tell us how the multimodal approach works? In other words, how is text useful, and how does the approach you described change when you provide multimodal input?
So you can have text being part of the input, just like you can have these random dice rolls. And it's just another type of knob that controls the generated data. When you have text, in order to make the output image look like it matches the text, you need to have some kind of supervision. And so the typical way you do that is you have a big data set of images paired with text that describes them. And you make sure that your image you generate for a given piece of text matches the supervised data that you've observed.
Wonderful. Professor Jacob Andreas, take it away.
Great. Yeah, thank you very much. So I want to pretty much pick up where Phillip left off and talk about how models that generate text work, sort of by analogy to the models that we looked at for computer vision. And I similarly want to start off with some pretty impressive examples. So here's one from this ChatGPT model that people may have heard about. We can ask ChatGPT to write a poem about the estate tax, and we get something that sort of looks like a poem and is definitely about the estate tax. It rhymes. It knows that face rhymes with race, and the right numbers of syllables are there, and so on and so forth. There's some political opinions being expressed here that we may feel a particular way about. But it's pretty remarkable that we have generative models of text that can do this at all. And we can take these same models, right, and use them not just to sort of give them instructions to do targeted generation of specific documents, but turn them into chatbots, right, and have conversations with them. Conversations maybe even in which they sort of appear to express things that look like desires or beliefs or particular attitudes towards the person who's interviewing them. So this was Kevin Roos at the New York Times interviewing this Bing chat model. So how do we find ourselves here? What is going on sort of computationally that allows us to build models that can do this kind of seemingly open-ended text generation? And so like Phillip, I want to give just like a brief overview of how some of these models work at a high level, skipping over many of the important details. Fundamentally, what language model, right? These ChatGPT models, these Bing Chat models, any of these other sort of language models that you've heard about, what these models are predictive text models. They're just like the thing that sits on your phone that sort of tries to guess what word you're going to type next when you're having a text message conversation with somebody. And so here's an example of a particular piece of text that we might want to complete from a famous book by Kafka. And the way in which we do next text or next word prediction with these models is we start by taking every word in the input and we embed it. We represent it as a point in some sort of high-dimensional space. So here I'm drawing the space as two-dimensional, but in practice these spaces are hundreds or thousands of dimensions instead. And some things that we notice as soon as we do this embedding process, similar words wind up close to each other, right? The names, Gregor and Samsa, are close to each other. If we put some other words in this space as well, the verbs are all going to be in one place, the numbers are all going to be in one place, maybe verbs that are more closely related to each other or close together, and so on and so forth. And so I can take my whole input sentence and I can put it in this space like this, representing every word as a point here. And what a particular style of language model called a transformer language model does is it picks up each of these points one at a time, and it looks at all of the other points around it using something called an attention mechanism, which you may have also heard about. And based on all of the other points that it sees in the input, it takes the particular point that it's holding, and it just wiggles it around a little bit in this space based on what it sees. And we can repeat this process for all of the other points that we started with in our input. And we can, in fact, repeat it over and over again, sort of multiple layers or multiple rounds of this wiggling around process until eventually we get an output that I've shown with a red dot here. And now, to figure out what word to predict next, I'm just going to go back to the original space in which I placed all of my words. I'm going to figure out which one is closest to that last point that I wound up with. Here that's drawn with a blue dot, and maybe that blue dot corresponds to the word pineapple, and so in this case our language model will predict the word pineapple. Now this is not a particularly good prediction for a next word that should come in this sentence, and so when we're training these models, the way we train them is we take real text, we look at the real word that came next, which in this particular document is morning, and we take that last point that we had, and we just move it around so that it's closer to that correct word morning than it is to any of the other points. And then we sort of push that movement back all the way through the entire network, moving all of the other points slower down around in such a way that we ensure that we have the final point that we started with. And if we do this over and over again on enough real text, we eventually wind up with, in this case, a transformer language model that can map from inputs and make good, reliable predictions about what word should come next. So why does this work so well? Why is just training this kind of next word prediction model, an autocomplete model like the one that lives on your phone, something that suddenly everybody is up in arms about? And it turns out that if you can do this next word prediction task really, really, really well, it implies that you can do a bunch of other important things, right? So being able to do good next word prediction certainly requires you to know something about the rules of whatever grammar, or the grammar of whatever language you're trying to generate text in, knowing how to make sort of verbs agree with nouns. They require you to know facts about the world, right? To sort of figure out that the most likely completion of this sentence about Barack Obama is Honolulu, you need to know not just something about English, but something actually about the world and what things are true in the world. And this applies not just to sort of high-level factual knowledge, biographical information, but even, in principle, common sense knowledge, like what happens when you drop an egg on the ground, and so on and so forth. And maybe saliently to some of the discussions that we're going to have later on, for important documents that appear many times in the training data, famous things like Shakespeare sonnets or Kafka books. Doing this task well actually requires memorizing some of the data that you were trained on. And maybe even more surprisingly, right, what these models learn to do is not just sort of encode these high-level linguistic features or high-level factual information, but actually much finer-grained things, right? So if you were to come across in your life a document that started like this, it said, a wadapu is a small furry animal native to Tanzania. Here's a sentence containing or using this word wadapu, and then giving an example sentence. And then I gave you another sentence, like to do a fardaddle means to jump up and down really fast. And I asked you to guess what was going to come next. You would follow the instructions, right? If you're trying to predict what comes next in some document that you found, and the document contains instructions, and you have some evidence that those instructions are going to be followed, you're also, in order to do a good job at this text prediction task, going to follow those instructions. And so something that just falls out of being a really good autocomplete model is being able to sort of follow, in principle, arbitrary instructions provided in text. And this applies not just to these sort of like one-off, use this word in a new sentence, but even sort of generation of seemingly realistic news articles where we say, here's a title, here's a subtitle, here's an article. We ask a model to generate the article, and what comes out is plausible text describing the article. I say plausible because, in fact, while this is a real event that the model was prompted with, the article is wrong. This last bit about the Christian Methodists in domination, no such a thing, or at least not in the context of this particular schism. And so while this looks factually plausible, it is not, in fact, factually correct. Maybe the sort of use case that we're most familiar with, or that we've seen the most of recently these days, is the use of these language models to actually build chatbots, right? And when we think about the kinds of software that's going to get built with them going forward, a lot of it probably looks like this, having sort of conversations with agents that are doing some work on the back end and talking back to us in natural language. But I think there's also, sort of a big wide world of other kinds of software that we're going to be able to build using this really good next word prediction capability, right? So imagine you're sitting in your text editor, and there was some magic button up in the top right corner that you could press where you could highlight a sentence, and the model would just rewrite your sentence to be more beautiful, or at least more sort of accurate English. And this is something that maybe we can do right now. We've had grammatical spell checking for a while, but there are many other ways in which you can sort of use these kinds of, or imagine these kinds of magic features in your apps, right? Saying things like, here's a passage, just shorten it, and being able to just slowly shrink your text the way you shrink an image in your image editor right now, and having the words pop out in the way that you want. And maybe even crazier things, right? Like taking a passage that you didn't look up any citations for and asking the model to just generate some citations for it. And I'll emphasize, right, related to that factuality thing right now, that this very much does not work. Even in sort of many of the best of today's models, they'll generate citations that are not true. But this is the kind of thing that we can imagine doing. And the important thing here, right, is this looks like a normal piece of software. And where there's language getting sort of generated and understood, it's all on the back end, right? So a sort of world in which code is written partly in natural language, and in which pieces of software are communicating with other pieces of software, maybe even using language as a medium. Obviously, there's a sort of a lot standing between us and that future. We've mentioned a couple of times these truthfulness and coherence issues that exist in today's models. Related to those are sort of basic safety and controllability things, making sure models don't embarrass us or harm users, and finally making sure that they can source their information correctly. And I will stop there.
Thank you, Jacob. Thank you, Jacob. While Professor Armando Solar-Lezama sets up, can you tell us how ChatGPT, GPT-3, and GPT-4 are related?
So ChatGPT, let's see. GPT-3 is a model from an organization called OpenAI that was trained, actually now a family of models of this transformer architecture that I just described that were trained sort of large scale but not particularly targeted way on a huge dump of data from the internet. ChatGPT is a version of that model that was specialized, that was fine-tuned in the same way that the portraits of you, or the model that generated those portraits were fine-tuned on a bunch of data showing examples of the kinds of chat interactions that they wanted the model to produce. GPT-4 is a newer version of this model that also has been sort of fine-tuned in a similar way, and unlike the previous ones, can make use of image data as well as text data.
Thank you. Armando, take it away.
Thank you. Thanks a lot. So one of the very exciting applications of some of these large language models is coding, software development in general. And the idea is actually arose very early on. The idea is, for a lot of these things, what you really have is just this model that is able to map a sequence of words or a string into another sequence of words. And that initially proved to be a really effective way, for example, of doing language translation. But if you have the ability to do that, you can also train it, for example, to answer questions. And then if you can do that, why not just take just a description of what a piece of code is supposed to do and turn it into the actual piece of code that will do what you're trying to do. And so you see that as the model started getting better and better in their ability to do this kind of sequence-to-sequence translation. For example, there was a big breakthrough in 2014 around using LSTMs in order to generate, to do language translation. And we actually showed that you could actually use that to, for example, correct students' programming assignments, right? Where you have relatively predictable text and you have a very well-defined task. A little bit later in 2016, for example, when attention became the next big step in how to do this, not too long after, actually, an alum from our group, Rishabh Singh, was part of this team that showed that you could actually use this to construct whole programs for relatively simple tasks in a fairly automated way. And it was around this time when transformers came about and that really the dam broke and you started seeing this explosion of research on how do we actually leverage this ability to map sequences of text to other sequences of text in order to generate code. And so code provides a lot of really interesting opportunities for these kind of technologies. On the one hand, we have a lot of data on actual software sitting out there in the world. We have the entire histories of versions of fairly complex applications. It's not just student code and their term projects. These are major applications that people use every day whose entire source code is sitting there on the web, ready to be trained, ready to train many of these models. At the same time, we have an entire toolkit coming from programming languages and compilers and program analysis tools on how to actually reason about these pieces of code. This is something very special about code and something that makes it very different from, say, translating from Spanish to English. In the case of code, you can actually run the code, you can actually test the code, you can actually analyze it for vulnerabilities. And so this is actually very, very powerful. On the other hand, code also introduces some really major challenges. On the one hand, code is brittle. Language generally has a level of redundancy where you can understand what people are trying to say, even if they get a few words wrong, right? Even the best newspapers and magazines out there, every now and then there's typos, and they just correct it, and nobody bats an eyelid. On the other hand, with code, single token or a small number of tokens can be the difference between a piece of code that works perfectly well and a piece of code that doesn't even compile, or even more dangerous, a piece of code that looks like it works perfectly well, but it also has a major vulnerability that might expose a lot of your private data, for example. Code is also very big, especially once you get to the space of commercial software. You are talking about hundreds of thousands, millions, tens of millions, and in some cases, even hundreds of millions of lines of code. And this is way beyond the scope of what even the largest models today are able to reason about and ingest in one shot. And so you really need to think a little bit differently about how you deal with the scale and the complexity of modern software. And code is also very diverse. You have different companies have different coding styles. They might use different libraries. Every major company has their own small ecosystem that might look very different from the code that you'll find on the internet. And the bar for accuracy, for many of the reasons that I said before, can be very, very high. Now, one of the most common things that you'll see today is that this basic capability of the language model is supplemented by essentially putting it in the box and surrounding it with further tools or techniques that allow you to do, from simple things like type checking or running tests to actually make sure that the code you're producing is doing what it's supposed to do, to somewhat more sophisticated analysis that you might want to run on the text, on the code. For example, there was this paper last summer that was very widely talked about on a system called AlphaCode that showed that these large language models could actually even place above the 50th percentile on a coding competition. And so these are actually fairly challenging programming problems in many cases. But the secret is to actually get the language model to produce tens of thousands of plausible solutions that then you can filter, for example, by actually running them. This is, again, something that you cannot do with natural language, but you can do it with code. And then actually checking which of these solutions that pass the tests are actually look like they're equivalent to each other. And therefore, we don't want to bother the user with lots of actually equivalent programs that are all wrong in exactly the same way. And so by doing this, you can actually go from tens of thousands of incorrect solutions to that one solution that actually solves your problem. Now, when we have these kind of techniques, one of the questions that people generally ask is, well, does that mean that programmers can just retire, that we shouldn't be spending all these resources teaching people to code? And I would say the answer is a resounding no. First of all, there are a lot of open problems that we would really have to address before we can really get to that point. There is obviously, as I said before, the problem of scale and how large modern code bases are and how much of that code base is sometimes necessary in order to really understand what you're trying to do. And related to that, there's a problem of locality. A lot of these models are pretty good at the problem of, here's something that I'm trying to do. What is the code that I need in order to do that? But a lot of time in development is actually spent not so much on the what, but on the where. Right? Here is this giant piece of code, and where are all the different places that I need to modify in order to actually get it to do what I'm trying to do? And this lack of locality sometimes requires some very high-level awareness of all the structure and the organization of this code. And that is actually a really big thing going into software development. And it's another problem that current models are really not addressing, which is this problem of how do we actually organize these thousands or millions of lines of code into logical units that support reuse, that support maintainability, that support understandability. None of these problems are probably unsurmountable, but they're also not problems that you're likely to see solved in the very recent future. Most important, though, is the problem of intent. There was this great cartoon on comicstrip.com back in 2016 where it talked about, yeah, there is an industry term for a project specification that is comprehensive and precise enough to generate a program. It's called code, right? And it's funny to look back, for example, at some of the early Fortran papers, for example, that talked about the Fortran automatic coding system, right? Now that we had Fortran, people would not have to code anymore. The code would be generated automatically, and it would be generated without bugs. And of course, now that seems laughable because that is now what we call programming, right? Writing these descriptions in these higher level languages. And we've seen this every time we see another big step in automation in programming languages. I think one of the really exciting questions is, how are these new kind of techniques going to transform how we program? But a separate, really interesting question to me is the applications of these capability beyond software development. All of a sudden, we have the ability. So these models gives us the ability of, for example, have questions and come up with answers. But there's a lot of contexts where the right thing to do is actually to take that question and turn it into a program that produces the answer. Because it turns out computer programs can be really good at things that large language models are not so good for. There was this paper last summer by a large team led by Ido Drury, where they showed that, for example, when it comes to solving university math problems, that if you gave them to, back then, the state-of-the-art models, they didn't actually do so well in solving these problems. But if all of a sudden you ask the model to give you not the solution to the problem, but a program that solved the problem, turns out there's a lot of Python libraries to do linear algebra. There's a lot of Python libraries to solve differential equations. And they're really good, much better than language models. And so by going through that step, it gives you this bridge between the informal world of natural language and the very formal world of code. You can do similar things, for example, where you can take data, and normally you think of, I have data, I'm going to use that to train a model that then translates inputs to outputs. But what if you use that data instead and going through the model to ask the model to give you a program that is going to map those inputs to those outputs? And now all of a sudden you have this symbolic representation that is able to do really exciting things for you. And we've actually done this in lots of domains. One recent one that was exciting was linguistics and understanding, for example, language morphology and phonology from small sets of words. So these are just some of the things that I think are really exciting in the space of program synthesis through language.
Thank you very much, Armando. So I hope you have a sense of how generative AI works and what some of the applications are, at least in the domains that we discussed. You all sent a lot of questions. There are about 2,000 people registered who are participating online. And so this weekend, I tried to synthesize the questions you submitted and organize them into technical categories and also societal categories. So the next part of our roundtable will aim to answer as many of those questions as we can in our time. And so I'd like to start with you, Phillip. And I want to ask you, how can we make the output of generative AI more powerful? In other words, how do you incorporate domain-specific knowledge and constraints into a generative model? And what can you do with that?
Yeah, that's a really interesting question, and I think actually it ties into Armando's talk, like how do you use tools that exist? How do you use a calculator and a language model? But maybe I'll answer it from more the computer vision graphics perspective, because it also comes into play there. So a lot of the models that do things more than making images, right now the models that make images are fairly unstructured. They're not using that. They're using domain knowledge, but less than we used to. But a lot of the models that make more complicated kinds of data, like 3D data or videos, or what's called a light field, which is just like the holodeck in Star Trek, these models that make visual data that's more structured, they still use a lot of domain knowledge right now. And that continues to be important to getting them to work. So they have the equations of projection and optics built into their objective functions and their optimization routines, essentially. So that comes in when you get to these more structured data domains. But I also think as you get more and more data, the data can kind of replace some of the domain knowledge, because the data will constrain what you're learning enough, and it will kind of teach you that domain knowledge. So we really can anticipate, as things go forward, you might need less and less structure, but right now it still remains important.
Cool. All right. Can you tell us more about how you control the style or the content of the images generated by a model, and what techniques are commonly used for this purpose?
Yeah, so this is something that I touched on a little in the talk, but I'll just emphasize again that I think that the most exciting thing to me about generative data is not that it can make photorealistic things, it's that it's controllable in a new way. It actually gives you new knobs. And maybe the most popular one right now is language. Language is just becoming this powerful interface to image generation. You can type something in and say, I want it to be in Van Gogh style, and it'll make an image in that style. But language is almost everything, Jacob, but not everything. There are some things that are hard to control via language, like exactly where I want to place the mountain in the background of my portrait on the wall, or whatever it is. And for those, there's other techniques, like you can make a sketch and input the sketch into the model and say that I want the output to match the sketch. So there's other types of control you can add as well.
All right. My next question is also technical. What are some of the common loss functions used in training generative models for image synthesis, and how do they affect the output?
Yeah, that's a great question, and maybe a little more technical. So most of the models, the diffusion models that I showed, and then the autoregressive models that Jacob showed, are both optimizing the probability of the training data under the model's distribution. So this is called a max likelihood, or max probability model. So most of these generative models are somehow trying to make outputs that are high probability under the distribution of the training data. And they do it in different interesting ways, but that's kind of the general principle. Maybe something a little bit different, just to add on to that, is that you might not only want to make high probability images, you also might want to make beautiful images or images that people think look realistic. So another kind of objective function that people are adding is models of human perception or feedback from humans. So yeah, basically that.
Okay, so that's great. So related to that, how do you evaluate the performance and what metrics do you use?
Yeah, so you can sometimes use those exact same loss functions as your metric. Like we might say the model achieves this likelihood, and that's just the same as the objective that you're optimizing. But you also might have something which is harder to directly optimize, like a user study, and then you'll need to have a separate evaluation. So usually the evaluation is something like, did you make outputs that look natural, look realistic, look high probability, or according to humans are useful and end up being used in downstream applications.
Cool.
And if I can just add on to that on the language side, even just coming up with these evaluations is an active topic, maybe the active topic of research right now. That I think there are a lot of cases where people have built benchmarks that show that models are achieving, human level accuracy at test X or text Y or something that seems to involve some deep linguistic capability, and then it turns out if you just, paraphrase all the examples a little bit, things totally break. And so, as much as figuring out, or maybe now more than figuring out how to train those models, just the question of how you reliably identify the failure modes is super important.
Yeah.
Well, on the orthogonal to that, Jacob, I want to ask you more about the transformer architecture. So the transformer architecture is at the foundation of this extraordinary performance we get today. And it all started with a paper called Attention is All You Need, the Transformer. And this paper proposes this new architecture that is based on attention mechanisms that is dispensing with recurrence and convolutions entirely. So Jacob, what is the meaning of attention is all you need, and why does it work?
So thinking back to kind of the history of neural models for sequence generation, right, which are quite old, much older than the current sort of generation of neural networks and going all the way back to Elman. The way they typically worked is that you have some sort of, representation of the state of a document as a single point in space, like I was drawing there before, and that every time a model sort of generates or observes a new word, it's going to just take that single point and it's going to move it around a little bit. And these models, which are called recurrent neural nets, are also quite effective as sequence generators. They were responsible for the first sort of round of big neural successes, including the ones that Armando was talking about. But they're quite hard to train. And the reason, or one of the reasons that they're hard to train, is that whenever you are sort of doing that backpropagation step of moving all the weights around in response to a single prediction you made, now you need to push that all the way back through all of the words that you've ever seen in the past. And sort of implementing that computational process efficiently is hard to do in a way that's numerically stable and slow.
So you get parallelism.
Yes, exactly. And so one of the things that these, and I guess even on top of those RNN models, one of the things that made that first generation of neural machine translation approaches really work was the introduction of this attention mechanism that didn't just have to pull information out of that state variable, but that could sort of look at arbitrary words in the past. And so what this attention is all you need paper was doing is saying, suppose we remove the state variable and we just have looking around at arbitrary points in the past. How far can we get? And it turns out that you could get performance that was at that time on par or a little bit better than the RNN models that we had at the time. But it's an interesting point that this was really motivated by parallelism concerns and by computational concerns. And I think it's an open question whether in the space of model architectures, there are other things out there that are maybe harder to train, but work as well or better than what we have right now. And being able to sort of scale computationally seems to be one of the major drivers of the architectural decisions that people make.
Awesome. So speaking of different ways of training and what this training actually means, I have a kind of a philosophical question for you. And this comes from the linguist Emily Bender, who is very worried about how we anthropomorphize ChatGPT. And so she created the following thought experiment to illustrate her point. So let's say you have two speakers of English, A and B, and they are stranded on a desert island. But then they discover that there is an underwater cable, so they can talk to each other. So pretty soon they start messaging, and they're pretty happy. But now, let's suppose that there is also a hyper-intelligent octopus, deep-sea octopus. Let's call this octopus O. And this deep-sea octopus discovers the cable and starts listening in and has the ability to detect statistical patterns over the exchanges between A and B. And pretty soon, the octopus begins to impersonate B while answering to A because it learned all the statistical patterns. Now, this ruse works for a while, and at some point, A gets attacked by a bear and launches an SOS message saying, hey, I'm being attacked by an angry bear. I have sticks. What should I do? But the octopus impersonating B fails to help because the octopus has no idea what a bear is, has no idea what sticks are, and does not know how to provide relevant advice like go grab some coconuts and rope and build a catapult. So Jacob, what is your opinion about ChatGPT and the statistical nature of communication? Is there anything beyond pattern matching?
Yeah, I mean, one could have a whole panel on that particular subject. And if you're interested in a whole panel on that particular subject, my postdoc, Anya Ivanova, is giving a talk at a conference at NYU this Friday on exactly the subject. But sort of briefly thinking about sort of meaning and how, the extent to which these models can build representations of meaning. That paper by Bender and Kohler was a super important one, was something that was certainly like very motivating for me in just asking these kinds of questions. And I think really anticipated a lot of the failure modes that we see even in like super, super big models today. And I think, maybe taking a step back, well, I guess I'll say first, that being said, I think the situation is a little bit more complicated, or at least that, sort of statistical pattern matching is a complicated thing to reason about. And taking a step back, the sort of like discourse around these big language models, it seems like there's a school of thought that sort of looks at ChatGPT and says, oh my God, this is like human level intelligence already. What are we going to do? Is this machine conscious? And this is just like manifestly not true of the models that we have today. It doesn't take very much interaction with them to realize that they're quite unhuman-like in both the kinds of things they know and the kinds of things that they can do. At the same time, I think there's also a school of thought or a way of talking about these models that say they're just shallow pattern recognition. They can't learn anything at all about meaning from the kinds of data that they have access to because it looks so different from the kind of data that people learn from, or because the architectures of these models is so different from people. And I think the situation is more complicated than that. That even though a big language model is trained in a very different way from any kind of human language learner, right, with only text as input and none of the sort of like rich social behavioral, perceptual context that we have access to. They're also trained at a much, much larger scale. And it seems to be the case that you can learn at least like the rudiments of a model of how meaning works and how the world works from text at that scale. And I think this was quite surprising to all of us who are working in the field, that we can get even as far as we can even if that doesn't get us all the way towards human level intelligence. And I think, thinking specifically about like the harms of these models or the harms from people being deceived by these models, certainly overstating their capabilities or, creating too high expectations about what they can do is dangerous. But also thinking of them as, just shallow pattern matchers that are never going to be able to fool anybody. I think also overlooks an important category of harms that we're going to see later on. And so, how much meaning you can get from text alone, like how much of about the world do these models understand, I think are questions that right now we just need to approach with humility because we don't really know.
Well, that's a good point. I want to ask you about an exchange I had this weekend. So a friend of mine sent me an exchange with ChatGPT. And the question was, tell me about the top 10 robotics people in the world. And so ChatGPT printed 10 names and why they were picked. And then my friend said, could you tell me about the next 10 people? And 10 more names were printed. And interestingly, there were 2 repetitions in the second group. 2 of the people listed were also in the first group, and the explanations were different in the second set of names than in the first set of names. What went on?
So, with all of these why questions in these big models, I don't know that it's like right now we even have sort of a deep enough scientific or certainly engineering understanding to give satisfying answers. There's a particular specific phenomenon in these transformer language models that they love to copy. And that just because of the way they're trained and sort of architecturally, they are very good at saying, oh, here's a string that showed up before that looks like it might fit into this hole that I have right now, so let me just pull it down. I would not feel comfortable offering that as the only explanation of what went on there, but it's at least part of it.
Got it. Armando, I want to ask you a couple of questions. And my first question is about developing state-of-the-art large language models. We've seen a lot of progress from industry. What would it take to develop large language models in the academy?
Computers, really big computers. I don't mean to be glib, but I think they're, this is a concern that a lot of people in academia are very concerned on, that the amount of compute that is the amount of compute that is required to create these models, and not just the machines themselves, but also the engineering around it to actually make some of these models run, put some of these research beyond the limits of what academics can do without very close partnerships with people in industry. And I think there is a risk that from the academic perspective, these things will start just being treated like natural objects that sort of come from above, and nobody quite knows how they were created, and our only hope is to sort of poke at them and see how they react and study them in that way. So I do think that it is very important to have the kind of investment that is necessary to make some of these techniques available to researchers in academia. I know that probably sounds self-serving, but it's true.
So today I learned that one of our peer organizations has just invested over $100 million in creating infrastructure that would support this kind of research. What do you think about this number? Is $100 million enough? Do you have a sense?
I honestly don't know. I think it's, especially the way these things work, right? It's not just buying the machine. You need to actually be able to have the support around it. Once you're talking about an asset of that
Exactly.
Of that size, it's not just the cost of the hardware that you have to consider.
But we really have to understand more about how they work. And I think that engaging in academic, industry, public, private partnerships will go a long way in our getting insight into these problems. Okay, here's another question for you. And this is about coding. And so it comes from one of our, from the audience. As generative code has arrived, how would this tool change DevOps? And how would this impact students who are still learning to code in school?
Well, so let me start with the second one, right? And I think in some ways, one of the things that is going to, one of the things that this is going to do is, I think there is going to be a change in what programming looks like. But I don't think the need for a lot of the skills that go into actually learning how to code are going to go away. If anything, they might actually become much more valuable in that a lot of the things that today are can be tedious and difficult will probably be made easier. This will actually make it more feasible to have coding-like interfaces to many more systems than what we have today, right? And it doesn't mean that all of a sudden there's going to be Python APIs for your toaster or for your refrigerator, but it does mean that this need for sort of algorithmic thinking and to be able to really leverage that control is going to now be come with a much higher payoff of I do think that there is a potential by making programming less painful and easier to do, that this will actually increase the scope of where we might see program-level interfaces. Now, in terms of DevOps, I think this is one setting where coding looks a little bit different from how it looks like in sort of general product development, where you might often see a lot more sort of one-off scripts, for example, to do certain kinds of tasks where some of these technologies might be especially helpful. At the same time, also the level of accountability that you need for some of these things is very, very high, right? Do you really want to trust a ChatGPT to just produce a piece of code that might take down your data center if it's not done exactly right, without having some experts actually look at it and make sure that this is going to do the right thing?
Amazing. All right, here's a question for all of you. What is the importance of scale versus the architectural model versus algorithmic innovation in the future machine learning? So what is most important, scale, architectural innovation, new ideas for the model?
I think all of the above, right? I think there's, one of the things that we have seen is that certainly scale matters, and that there's a lot of things that scale will buy you. But I don't think that it's going to be enough, right? So, ChatGPT, you were talking about, a window of around 4,000 tokens of sort of how much things they can pay attention to at one point. Right now, you're starting to see things on the order of 32,000 tokens, right? That is much, much bigger. It's still tiny compared to the scale of a large-scale software application, right? So are we going to get there just by scaling up? Probably not. I think we're really going to need some new ideas. I think scale buys you a lot, but it's not going to buy you everything. That's my stake in the ground.
Phillip and Jacob. Phillip,
maybe
it looks like you want to jump in.
Sure, yeah, one thing I can add. So yeah, I agree. It's really all of the above, but one way that people have started thinking about it is analyzing algorithms in terms of how much performance you get per data point. So this is called a scaling law. For every new data point you add, how much performance do you get? And then if you're working on the algorithms, you're just trying to make it so they scale better with data. They get better performance faster with more data. And it's really the two combined that get you performance. So data and scale is not going to go away, in my opinion, but we can think of it as how do you get more out of the data that you have? And every new data point that comes in will give you just more and more and more.
Jacob, you want to add?
Well, I guess just to make a pitch specifically for algorithmic innovation, as several people have been alluding to so far, there are a lot of applications where we want to use these models, but where we also want, precise, verifiable outputs. And I think there are reasons to expect that purely neural models are going to make it very difficult to provide the kinds of guarantees or the kinds of verifiability that we want. And there's a whole, incredibly exciting category of, and I think we're seeing this already, right? That there's a lot of interest in taking these big language models and augmenting them with web search, with calculators, with the ability to write one-off Python programs. And I think figuring out what that interface looks like and figuring out what sort of general purpose coding or sort of general purpose inference, structured inference in a language model looks like is a really interesting question.
For safety critical applications like robotic control, we need safety guarantees. So what are your ideas for getting there?
Well, I mean, I think thinking about writing code that is then verifiable is a good path towards doing that, right? That these models are good at coming up with symbolic solutions to problems. The solutions are not always correct, but like Armando was saying, you can sample 10,000 of them and then verify them after the fact. And so as long as we continue to make progress on formal verification, the set of applications where you can say, okay, here's my informal specification, language model, formalize it, and then sort of do your verification in that space becomes a lot bigger.
Yeah, so there's this whole space of techniques that we and others have been working on now around neurosymbolic reasoning, and really how do you leverage the things that these models can do really, really well with the things that are really just best done symbolically, where you really need that reliability, where you really need that predictability, and how do you make them work together in a way that is productive?
Cool. Well, I'm very eager to make progress in this area because I want my robots to learn. Okay, generative AI can be used to create deep fakes. What can we do about this? Are there technical solutions?
Yeah, I think I can comment on this a little because we've worked on it a bit. It's a huge question right now, obviously. There are a lot of technical methods that try to deal with deepfakes, that try to detect deepfakes or watermark images so that you can verify that they're not faked. And yeah, my group has worked on that. A lot of other groups have worked on that. I think that it's kind of an arms race right now. It's kind of a case where the next model that comes out, you can maybe protect against it, but it's very hard to protect against all future models. So it's a bit of the state. It's a little bit more like computer security right now. So we have a lot of tools, and the landscape changes quickly, and we just have to adapt to that. I think that the direction that I find most compelling longer term is methods that actually do some kind of digital signature or watermarking. They actually intervene in the content creation process, as opposed to methods that just try to detect if something's been faked from an unknown process. So for example, I think OpenAI is putting in some of their models, or thinking about putting in some of their models, subtle watermarks, so that ChatGPT, anything it creates, there's some statistical pattern in the things it creates. So any ChatGPT creation could be detected. Now that's not completely solved, but that's a direction I find pretty interesting.
That's very cool. I've heard about that, and I'm very excited. But is this enough? Or should we consider laws that punish the harmful use of generative AI like we punish the harmful use of other tools, like knives and guns?
Yeah, so I think I have less expertise on that, but personally I think that yes, we need to integrate this into the legal framework. That's just seems completely true. How to do it exactly is very unclear to me. But yeah, I think having some kind of regulatory framework around generative AI and deepfakes is going to be coming. A lot of people have been talking about that.
Armando, you look like you want to jump in.
I think one of the things to watch out for here is that this is a problem that is not going to be solved purely with technical solutions, right? We can sort of provide the space of solutions and also raise awareness about what the capabilities of these models are, right? Because I think it is very important for the broader public to be aware of what these models can actually do. But I think at the end of the day, this has to be a broader conversation. This should not be a conversation that is limited to technologists, because it is a pretty big social problem that goes beyond the technology itself.
So I have a related question from one of our students, and I'm going to read it. As researchers, how do you navigate the profound ethical challenges raised by current generative AI products? Those challenges include plagiarism or theft from the original human creators, biased or otherwise dangerously faulty output, economic impacts on workers, as well as overwhelming our existing social systems with AI output. As a CSAIL PhD student, I struggle a lot with working in a field where the very technological advances I'm striving to contribute to can also create so much potential to harm. What do you think are the moral stakes to creating a generative AI world? And how should we researchers be guided by those stakes when choosing problems to work on? Jacob, you're nodding.
Well, I mean, I think there are a lot of problems to choose them that are exactly related to sort of understanding and mitigating these harms immediately, right? I mean, you're looking for sort of interesting, meaty, technical, PhD-worthy kinds of projects, like this content attribution problem in models for computer vision or language processing models or whatever is exactly such a thing, right? And I think there's many categories like that. How do we make these models more controllable? How do we make these models more truthful, more coherent, better, more editable, right? Making it possible for people to remove their personal information or their training data from models after they were trained. All of which are, I think, like the most urgent problems required to make these models better, but that also contribute directly to mitigating their harms. So, there's some large category of questions that are around how do we train a bigger version of a language model. It's not clear that those are even interesting sort of artificial intelligence questions in the first place. And the questions that are interesting, I think, are the ones that give users more control. That being said, I think there's also lots of avenues for people in the research community to, like Armando was saying, sort of get beyond the technical piece of this and engage with policymakers, engage with educators outside of computer science and other people who are affected by these technologies.
Anybody want to add? I can move on to the next question, otherwise. Armando.
I mean, I think as technologists, the most important thing that we can do is to speak clearly and truthfully about what these models, where the technology actually is, where we see the technology going. I think it is important for researchers not to shy away from applications that might have some of these dual-use nature, because I think it is very important for people in the open community and in the open public to actually know what are some of the things that can happen and what are some of the things that an unscrupulous actor can do. Now, of course, that has to be done carefully and it has to be done ethically, but I don't think we can shy away from really pushing the research and really getting to the bottom of what it is that these models can actually do.
Phillip?
Yeah, I completely agree with all that, and I do think the stakes are high. I think that in addition to working on technology to mitigate harms and integrate AI in a positive way with society, the way I kind of think about my role is my job is not to create AI. My job is to understand AI, is to understand intelligence, to understand it scientifically, mathematically. And I think that's a role that universities are really well suited to play. It's what I think a lot of us care most about, really understanding how these things work, how intelligence works, what are its possibilities, what are its pitfalls. And that's a role that I think sometimes requires making the technology to some degree and playing with technologies that exist. But I think that's kind of just positive overall. Understanding these things is critical to mitigating the harms as well as making them do good things for us.
Thank you for that. Okay, 2 more quick questions from the audience. Are ChatGPT-like tools a threat to software developers like me, who work mostly on web applications?
I would say no. Again, I think there's certain things that they're pretty good at doing, and I think it will certainly be the case that developing and doing these kind of web applications is going to get much easier. But a lot of the work that goes into that is not so much the nuts and bolts. I mean, there's already lots of fantastic tools for people who know nothing about programming to go and build highly functional websites and do many things. And in many ways, the value that humans bring to this process is being a fellow human being and understanding what are the needs of the users, understanding what it is that they're going to be able to, maybe what are the things that they're going to struggle with. And that kind of human understanding is still today fairly hard to replicate.
What should I do to make my career AI-proof so that AI couldn't replace me?
Learn AI.
One category that AI has not yet touched that much and humans are way, way better at is all the physical stuff. So robotics, manipulation, and this is kind of...
come to robotics.
Yeah, come to robotics, basically.
Well, no, take up carpentry.
But really, yeah, take up blacksmithing, carpentry, plumbing. These are things that could be around for a while.
All right, so many science and technology leaders have sounded the alarm on serious threats from AI. And in fact, in 2016, Stephen Hawking asked, What does it mean today to properly manage AI for us scientists? Are we the right people to really manage every aspect of generative AI, especially the societal and economical aspects of our societies? Hawking also said that the biggest threat from AI comes from the people they serve, from the consciousness that set their goals. Now, generative AI provides tools to think faster and more efficiently, but how do we ensure that these tools help us to think more benevolently?
Unfortunately, we cannot. I don't think we can. It is a very powerful tool, and I do think that when used for the right purposes and in the right context, I believe that it's going to be an extremely useful tool in helping us address a lot of the really challenging problems we have to deal with, from the energy and climate to it can be a really powerful tool to address even social problems, as long as there is the social support structure behind it, right? These are not benefits that are going to come from the technology alone. You need to have the people who actually want to solve those problems be able to leverage those technologies. And there are also going to be people who have other agendas that are also going to be trying to leverage them as much as possible. And I think that is why it's so important for the broader public to learn about the technology, to become familiar with what the technology can do and what it can be used for, so that it doesn't become this elite thing that only a handful of powerful actors can leverage.
That's right. So I agree with that. We need the public to not necessarily understand the hairy details of what things work, but what can you do? What can't you do? What should you do? What shouldn't you do? And what kind of guardrails need to be put in place in order to make sure that we answer the should and should not correctly. So that's a very important thought for the future. All right, so here's another question. Data represents the new gold rush of the 21st century for AI. If anyone can change or transform the data according to their will, how can we ensure generative AI does a proper job? And also, who protects this data and makes sure the data is safe and not misused? So I have my data, generative AI can change it. How can I get a hold of that process? How can I control that process?
So,
Phillip,
I can comment.
You look like you can comment.
I don't have an answer, but I have a comment. So I think it's kind of related to deep fakes that, if you can manipulate the data, we might lose touch with reality to some degree. How do you mitigate against that? And one thing I've gotten quite interested in is that a lot of these models are now being trained on other models. So it's models trained on models. It's models trained on synthetic data. And you might have this whole ecosystem of AI systems that are, you have one base language model that produces outputs that then get input to another model that trains on, the examples provided by GPT-3 or 4, and you get this stack. And so I don't know how to deal with that, but I would say that we're starting to look at how that kind of model trained on model can propagate errors and what you might want to do with that. So it's something I'm thinking about. I don't have a solution right now.
But it's clearly something.
It's something that's happening.
It's happening. We need to think about that. We need to put our arms around that issue. Yeah. Jacob?
Well, and this is also a case where I think or at least part of what we need is really just like a regulatory framework for allowing people to determine how their data gets used, right? And that right now, a lot of these models are sort of trained from data that was indiscriminately scraped from the internet. The sort of copyright status or fair use status of training data and things that look like bits of trainer that show up in the output is still like very much an open question. And I think there's both a need for a framework by which people can sort of say affirmatively, I'm allowing people to read this website but not to train their models on it, and then technical solutions that allow people to verify that those guarantees have been satisfied, and that, for model makers to be able to certify that they haven't trained their data in a particular way. And one piece of this that's sort of especially scary, talking about or building on what Phillip was saying, right, is that a lot of the internet has already been slurped up into GPT-3, and so if future models are going to be trained on the output of GPT-3, it may be very difficult to remove from that data that people no longer want to be included.
I think, again, this is a social question, right, that we're probably the least qualified people to answer. However, I think it is important that those debates around some of these issues are actually technically grounded, and that they incorporate a certain awareness of how these things actually work. For example, if you have a database and there's an entry for you, it's very easy to say, oh, this entry should not be there anymore, delete it. If you have a model, and somewhere in that model, in the weights of that model, is incorporated some data that came from you, it's actually not really that feasible to go in and say, oh, nope, that's the Daniela neuron, and we should knock that out. And
never knock it out.
Well, but then maybe we need to create pressures to create such models so that you can do that.
Yeah, and I think this is where you really need that interaction between the technical and the social aspect.
So I want to pivot and ask you about art. I love my portraits, but my question is whether creative art is only the result of statistics and mathematics on data, or is there something else going on in long-lasting, great works of art? For example, would a young Mozart today be able to create and write music the way he did when he was only 5 or 8? Now, Mozart did not know every piece of music ever written before him, and he was very young. He was only 5 and 8 when he wrote brilliant, genius music, all based on his 5 senses. So how should we consider the products generated by generative AI as art? And do you think AI is capable of capturing emotions or commentaries on society or other aspects that you might associate with great works of art?
I mean, I think what you're really asking is, a great work of art is really determined by the impact it has on the observer. And one of the things that if you really want to emulate that, what you need is something that is able to model and capture, how do people think? How do people feel? And what are the things that do that? Now, at one level, you could say, well, we can kind of do that. And, certainly movie producers do a lot of that when they're trying to, pull at people's heartstrings and, elicit a certain reaction. And nowadays, a lot of that is fairly data-driven. I think some of that is, just the cultural context, right? And I think evidence suggests that people are probably more willing than you might expect to ascribe feelings and emotions to robots. So I think it's doable, but I don't think it takes anything away from the creative process of people actually communicating what they feel, right? Because at some level, I really don't care what a robot feels, and I care about what my fellow human beings feel. And so, could robots produce art? Yeah, probably. Would I care to? Would I enjoy it as much as something that I know came from somebody I empathize with as a fellow human being? Probably not.
Well, so I think we're going to have a debate on creativity and AI another time. I have one more question for all of you, and then we will wrap up. And so my final question is about discovery in science, and in particular, anomaly detection is one of the benefits of generative AI, but many scientific discoveries arose from actual anomalies or scientific intuition. And for example, Fleming discovered penicillin by chance, by serendipity. So will generative AI allow the researcher to think outside of the box or guide the researcher more inside the box? And what will the consequences of data-driven and less intuitive invention be?
Yeah, so I don't know. I think that it could go either way, but I would say that in my personal experience over the last year, the moments that I felt the most creative and most inspired, several of those moments have been interacting with the latest interesting new model. And at least for me, playing with DALL-E when it came out or ChatGPT, I did feel like it was more of an aid to my creativity than something that was narrowing what I could think about. So I don't know, maybe like subtly I'm being, going into the mainstream way of thinking because the model only knows one way of thinking, but that's not how it felt to me. And I do think that a lot of like really interesting ideas can come from collaboration with these models, and that has been my experience.
I can't remember which model it was, but recently, prompted one of them to generate a description of our research group for the homepage, and it spit out a list of 5 papers, one of which has already been written by somebody else, and which it wrongly attributed to us, and 4 of which are not real papers, but sounded quite interesting. So I think
So you have some ideas, huh?
No, and I think in a serious way, like there are. Exploration is hard, and there have always been tools for structured exploration, and whether that's like the whatever cards they give you at design agencies to do your out of the box thinking, or whether that's tarot cards or whatever. Like we've always had tools for helping us sort of explore in the space of possible ideas, and if these are better tools for doing that, then great. And if they're not currently better tools for doing that, then I'm sure people will find ways of turning them into them.
I would never bet against human creativity, and I think I have no doubt that there's going to be lots of people who would find really creative ways of using this technology to develop things that we can only imagine. And I'm actually pretty sure a lot of them are going to be here at MIT.
I like that. I like that. Okay, my closing question, very, very fast answers from all of you. Can you give us your favorite example of using generative models in business?
I don't think I have one.
Jacob, Phillip?
Like things that are being used today, or potential future
Whatever
uses,
you like.
or
Whatever you like.
I mean, like I was alluding to in the talk, I'm generally quite excited about the idea of sort of, language as a tool for building software, and not just sort of slapping a chat interface on everything, but using the affordances that we already have that sort of like decades of HCI research have often told us are better than text. And using them to do things that right now we only know how to specify in text.
Phillip?
Yeah, I don't know the degree to which this is yet being used in business exactly, but I think one of the most exciting things to me is the potential, which we didn't talk about, of these models to make new molecules, to make new fabrications, to make new architecture, to make new things that are not just pixels and text, which is really cool, but now starting to get like, we've kind of seen it, it's going to be super cool, but to make really new physical stuff. And that's starting to come online now. I don't think it's yet really hit businesses, but to make a new drug that can cure some disease, that's one of the ones that's most exciting to me.
That's pretty extraordinary. Well, mine is about summarization. So mine is about taking entire libraries of text, summarizing them and providing references. So for instance, imagine being a lawyer, or imagine being a law student, and imagine having to read entire libraries of cases, each one described over thousands of pages. So now imagine having a case in front of you and getting one of the models, one of these language models, to kind of summarize for you what all the related cases might be. Where should you look to get the right references? And I think that we can imagine applications like this in many fields, not just in the legal field. I'm very excited about that. I'm very excited about the idea of using these models as a kind of an assistant that can go and pore over huge amounts of data, coming up with useful suggestions for me to act on. these models are not ready to act autonomously in the world, but these models can really help me with patterns, with information that it would take me way too long to get at.
So maybe just to...
now you have an application. Okay,
no,
okay.
So what I was going to say is I think all of these are super exciting, and I hope they're not, they don't just stay as business applications, right? I would really like to see a future where all of these are, widely applicable, not just to people trying to make money.
So we have come to the end of this roundtable discussion on generative AI. I hope you all have a better idea of how generative AI works, what some of the limitations are, what some of the opportunities for business and for research are. And I, for one, feel like the more we study about AI, the more we understand that we have so many questions that we still need to understand, that we still need to research. And we have questions about intelligence and questions about ourselves that we really need to answer sooner rather than later before AI plays out without a careful hand. And so moving forward, it is essential that we continue to explore the topic of generative AI, that we collaborate with each other to advance the field. So let's give our brilliant panelists a big round of MIT applause.